Okay, so today we're going to talk about calculating derivatives. Can everybody hear me? Yes, it's loud enough? Okay, so in the past couple of lectures we've introduced the concept of derivatives, and we've said what it is in terms of limits, right? And we also said intuitively what it is. It is basically a function that describes the slope of another function, right? So as it turns out, part of the genius of Newton and Leibniz was not just finding out the idea of the derivative, but as it turns out, the derivatives can be calculated very efficiently for many, many functions. So there are actually rules to form the derivative of a function that usually don't involve the concept of limit. Basically, the idea of the limit is still in there, but you don't need to recall limits every time that you do the derivative. You just remember the formula and you plug it in. So it's perfect for undergrads. No need to think. You just follow your nose. So this is 3.1 and 3.2. This is calculating derivatives. Okay, so we're going to learn first the derivatives of special functions. Special functions. Okay. So recall that if f of x is equal to x, okay, what is the derivative? Okay, how do you know? Well, just plot the function and notice that it's a straight line with a constant slope. The slope is equal to 1 at every point. So the derivative, f prime of x, is equal to 1. Okay? Great. What about the function f of x equal to, let's say, 1? That function is constant equal to 1. Okay? So the derivative is 0. That's right. Okay, so what about f of x equals x squared? 2x. Okay, the derivative is 2x. How do you know? Well, we actually did this before. Let's see. So the derivative at 0 is equal to 0. You can see that the function is flat. When x becomes slightly bigger, like x equals 1, the derivative becomes positive, and when x is negative, the derivative is negative, right? So in fact, as x grows larger and larger, the derivative becomes bigger and bigger. So as you can see, it makes sense that the derivative is something like 2x. In fact, we already computed it. We actually calculated the limit in this case, I think last time or 2 times ago, and the derivative is indeed 2x. Okay, so in general, if f of x is equal to x to the n, then f prime of x is equal to, as it turns out, nx to the n minus 1. Okay, so that's a very, very useful formula because it can allow you to calculate the derivative of a lot of functions. So for example, if f of x is equal to x to the 5, then what is the derivative? Well, let's first figure out what is n.
5.
N is 5, that's right. So f prime of 5 is equal to 5x to the 4. Right?
Yes.
Awesome. Yeah. Okay, this formula can actually be used also when the power is not apparent. For example, you can think about a function like f of x equals to square root of x. Okay? And that can be written as a power, namely x to the what?
1/2.
X to the 1/2, that's right. Okay, great. So that means that n is equal to 1/2, and that means that f prime of x is equal to 1/2 x to the
Negative
1/2 minus 1, which is 1/2 x to the minus 1/2. What is 1/2 x to the minus 1/2? That is 1/2, 1 over x to the 1/2, right? And this can be written as 1 over 2 square root of x. Okay, fantastic. So, I mean, for the beginning, if you haven't seen this before, I would recommend using the formula, but then at some point it's better probably if you just remember that the derivative of square root of x is 1 over 2 square root of x. But it's okay, we're going to be talking about several different formulas today, so basically if you learn this formula for today, that would be great, and that's quite sufficient for a lot of purposes. Let me give you another example. If f of x is equal to 1 over x, once again you think, well, what's that got to do with power functions? Well, easy, right? This is the same thing as x to the minus 1. Right? So n is equal to what?
negative.
Exactly. N is equal to minus 1. So f prime of x is equal to minus 1 times
Negative 2.
x to the minus 1, which is minus 2. That's minus 1 over x to the 2. Okay, wonderful. Okay, so as I was saying, this is a very convenient formula because you don't really need to think. I mean, that's not just good for you guys in a midterm, it's good for anybody. It's very convenient because you don't have to, there's no decision to make, there's no limits to write. You just plug in the formula, that's it. Okay? So question, what do you think this formula works with? Does it work with any natural number? Does it work with n equals 0? Does it work with all negative numbers? It seems like it works with a lot of numbers because, for example, here we applied it for a positive natural number. Here we used it for a fraction. Here we used it for a negative number. So in fact, the formula works for, what do you think? So this formula, who says all integers? Does it work for all integers, including 0? Does it actually work for 0? What do you think?
It cannot work for rational.
Let's see. If n is equal to 0, then this is x to the 0, which is 1, right? Okay. So what is the derivative of let's apply the formula. This is 0 times x to the n minus 1.
0.
It's 0 times something, right? It's 0. Okay, so it seems like it does work actually, because the derivative of a constant of x to the 0 is 0. Right? So it works for 0, it works for natural numbers, it works for negative natural numbers, it works for rational numbers. In fact, it works for all real numbers. All real numbers. N. Okay, right now we actually cannot prove that, and I believe the book will talk a little bit more about it, about how this can be proved for arbitrary real numbers n. But for now, let's just think about it using in this particular context, like 1/2 minus 1 and so on and so forth. If you wanted to prove every one of these things, you can actually do it. You can actually do one by one any of these, or you can look at a more general proof that I think works for all integers in the book. Okay, fantastic. So that's the rule for power functions. What about exponential functions? Let me write this in a different page. So exponential functions are of the form f of x equals a to the x. Okay, for example, 2 to the x. So let's think about the derivative. The derivative f prime of x is equal to the limit when h tends to 0 of f of x plus h minus f of x divided by h. Okay, and when you write down the definition of the formula of this function, you get a to the x plus h, right? But x plus h in this case can be written as a to the x times a to the h, right? Minus a to the x divided by h. Okay, great. So can we simplify this expression? What do you think?
You can rephrase it.
We can rephrase it, yes. How do we rephrase it?
A power x came out.
Exactly. We can factor, this is called factoring out. Factor out a to the x. So I can factor out a to the x and I can bring it outside the limit. And this is equal to a to the x multiplied by the limit h tends to 0 of a to the h minus 1 divided by h. Okay. Now, does anybody recognize what this expression is? Remember that in the exam, I asked you to look at a limit and look at it and search for some derivative that is equal to that limit. So let's think, is that limit some kind of derivative, the derivative of something? The derivative of a to the x at what point?
0.
At 0, that's right. So that's wonderful because that means that this is equal to a to the x times f prime of 0. Think about it. If I wanted to write f prime of 0 will be the limit when h tends to 0 of a to the 0 plus h minus a to the 0 divided by h. And that's just this, right? So that means that the derivative of a to the x is just a to the x times a constant. What constant? F prime of 0. Now, recall that the number e is defined such that. Do you guys remember what the definition of e was? Let me remind you what the definition of e was. When you plot the function e to the x, you take the slope at 0, you take this point here, you take this slope, and the slope was supposed to be equal to 1. At that time, it sounded really technical and rather silly. Why would you make such a big deal of a slope at 0 being equal to 1? But if you remember, that's what we did. We said there's different, for example, if you do 2 to the x, you get one slope at 0. If you do 3 to the x, you get a different slope at 0. And if you choose the number just right, e to the x, then the slope is equal to 1. Less than, well, okay, we said slope is less than 1, bigger than 1. If you choose e to the x, it is just exactly equal to 1. Okay? What does that mean? It means that if f of x is e to the x, then f prime of 0 is equal to 1. Right? Because f prime of 0 is the slope at 0. So we have this very interesting formula, or at least surprising formula, that if a is equal to e above, and then f prime of x is equal to e to the x times 1, because this f prime of 0 is equal to 1 is equal to e to the x. Okay? So basically, we have the formula that if f of x is equal to e to the x, then f prime of x is also equal to e to the x. So I remember hearing this story when I was a kid, that there was this party and a bunch of mathematical formulas were partying, and then in comes this guy and say, I'm going to derivate everybody, and then everybody starts running, and this guy starts derivating everybody, and then this one kid there doesn't care, right? And he's like, you don't care, I'm going to derivate you. And he says, oh no, but I'm e to the x. So that's a joke. Anyway, so I didn't understand the joke until I figured out this out, like the derivative of e to the x. So now you know. So there you go. So the derivative of e to the x is e to the x. Okay? Do you think there's any other function whose derivative is itself? Who can think of another function whose derivative is just the function itself? Yes?
F of x is equal to 0?
That's right. F of x is equal to 0. It's also they could also party without a problem, because the derivative is still just 0. But as a matter of fact, the e to the x is the only function. I'm pretty sure this is true. It's the only function. No, that's not quite true. It's almost true, but not quite. For example, what's the derivative of 2 times e to the x? 2 times e to the x, yes. So, I mean, if you don't count multiplication by constant, I believe that this is the only function with that property. Okay, great. So let's move on to the second part, which is new derivatives from old derivatives. Okay, so here's the idea. You have a function, and you already know how to derivate it, and you create a new function from that old function. So for example, suppose that you have a function f of x, and you want to find a derivative of a constant times f of x. And this is basically the example we just said with 2 times e to the x. So the derivative of a constant times a function is c times the derivative of the function. So how do I say this in words? In case that the notation is a little funny. Notice that we changed from Newton notation with f prime, we changed over to Leibniz notation, d dx. Okay? And here you can actually see clearly the problem with the Newton notation. Every single time we've had to write, if f is defined like this, f prime is this. If f is this, f prime is this. If f is this, f prime is this. So there's always 2 lines you need to write. Okay? The other notation, this notation, allows you to write the function you want to derivate right there in the same line. Okay? So in words, what this means is that if you multiply a function by a constant, say by 5, then the derivative of that function it's just equal to 5 times the old derivative. Right? If you multiply a function by 5, the derivative gets multiplied by 5 too, basically. Okay? So we can actually prove this just to see what kind of proofs this looks like. The derivative of the function c times f of x, by definition, is the limit when h tends to 0 of cf of x plus h minus cf of x divided by h. That's just the definition of derivative. And we can factor out the c. We can write this down as c times the limit of f of x plus h minus f of x divided by h. And this is just c times the derivative of f. So the proofs themselves have to use the definition of the derivative using limit. Basically, you're opening the hood. But for using the formula, you don't need to go back to the original definition. Okay, here's another formula. The derivative of f of x plus g of x is the derivative of f plus the derivative of g. So that also is very convenient. If you want to find the derivative of a sum, then you just break it down into two, find the derivative of one term, and add it up with the derivative of the other term. Okay, so for example, let's say that I want to calculate the derivative of 2 e to the x plus x to the 7. Okay, so this is equal to, because of the addition formula, this is equal to the derivative of 2 e to the x plus the derivative of x to the 7. But this is just because of the, let's say, the product, the constant multiple formula. This is equal to 2 times the derivative of e to the x, which is e to the x, plus the derivative of x to the 7, which is 7x to the 6. So there you go. Okay, so those were basically the easy formulas. I'm going to mention something that this formula, the so-called addition formula, also works this addition formula also works for subtractions. So for example, the derivative of f minus g is equal to the derivative of f minus the derivative of g. Okay. I can actually, we can write down a proof of this. It's not hard. Sure, let's do it. How about this? Let's do the proof of the minus one. So proof the derivative of f of x minus g of x is equal to the limit when h tends to 0 of f of x plus h minus g of x plus h. Okay, and the whole thing minus this function evaluated at x, f of x plus g of x. Why did this minus turn into plus? Because it was a minus inside of a parenthesis. Okay, the whole thing divided by h. But we can write this down as the sum of two limits. In this case, we can break this down into two parts. We can take this part and this part, f of x plus h minus f of x divided by h. And then we subtract g of x plus h, and this plus once again turns into a minus. And we break it off into a different limit. Let's see, so this is g of x plus h minus g of x divided by h. So notice that this minus turned into a plus, but then when I break it off into two fractions, it turned again back into a minus. You see, if I wanted to write this again as a fraction, I'm writing minus this whole thing, so this becomes minus g of x plus h plus g of x. Okay, so you get back this sum over here. The business with the minus is really not that relevant here. We can also just write plus all over the place and it will be the same thing. But the bottom line is that you can break this fraction off into two parts, and by the rules for limits, right, then this limit of this sum can be broken down into two different limits, added up together. This is just the derivative of f of x minus the derivative of g of x. Okay. So now we can talk about something called the product rule. Which is a formula for the derivative of a product. As it turns out, the derivative of the function f of x times the function g of x can be written nicely in terms of the derivatives of the individual functions. Does anybody want to try? You guys are not necessarily supposed to know this already, but if somebody knows it, do you want to try?
It suggests the formula, it's the first gx time. No, it's the fg derivative of gx.
Okay.
Plus g times the derivative of fx.
Excellent. And that is the product rule. Thank you, sir. So basically, you take the derivative of one function, multiply by the other, and then you take the derivative of the other function, multiply by the first. So I would like to bring something up with a notation. If you write the derivative of f times g, okay, this by itself is bad notation. Why do you think this is bad notation? Okay, what could be a possible confusion if you just write the derivative of f times g? Yes?
Because you're just assuming that you're just taking the derivative of f of x and not the whole function itself.
Exactly. So in this case, I would mean the derivative of just f of x and the whole thing multiplied by g of x. Right? So if you just do derivative of f multiplied by g, it might look like it's the derivative of the whole thing. You see? So when we write it over here as f multiplied by the derivative, we're consciously avoiding this notation problem. We're writing it as f of x times the derivative of g, and that way it's completely clear that the derivative only applies to this function. Do you see how if we flip the order of this product, it would not be very clear what you mean, right? Okay, so for that reason, we tend to leave the derivatives for the last part of the product. It's just a way to create less confusion for yourselves. And over here, I wrote a parenthesis to indicate that the derivative applies to the whole thing. So if you wanted to write it like this, you would probably have to write d dx, and then you write a big parenthesis here around the f, and then you multiply the whole thing by g. Okay? That would be an option, but I think in general it's just better, especially when you're using this kind of notation, this Leibniz notation, to write the derivative in the end. Okay, so all right, so as an example, let's say that we calculate a derivative of e to the x times x squared plus 2x to the 4. What is that? Well, using the product rule, this is equal to what? Well, e to the x multiplied by the derivative of the second function, which is x squared plus 2x to the 4. By the way, I should probably write, because of what I said before, I should probably write a big parenthesis around these things here. Right? So, and here I probably should also write a parenthesis to indicate that the derivative applies to the whole thing, not just to x squared. Plus x squared plus 2x to the 4 multiplied by the derivative of e to the x. Okay? Great. And what is that? So that is e to the x multiplied by
8x.
Okay, so let's think about it. We have a sum, so technically we have to use the sum rule, right? If you haven't done this before, you might first need getting used to the sum rule, but you can write this down as the sum of the derivative of this and the derivative of that, right? What is the derivative of x squared?
2x.
2x. What is the derivative of x to the 4?
8x.
4, just by itself, x to the 4, the derivative of 4 is 4x to the 3. Okay? And we're going to leave the 2 in there. Okay? Plus, oh, sorry, this should definitely have a parenthesis. Plus x to the 2 plus 2x to the 4, 2x to the 4 times the derivative of e to the x, which is e to the x. That's right. Fantastic. So, and that's it, right? I mean, if you want, we can put it all together, write it as e to the x times something. Sure, let's do it. E to the x times, and then we write something like, in decreasing order of power is 8x to the 3. Oh, I'm sorry, there's actually, let me, okay, let's not do it in decreasing order of power. So this is times 2x to the 4, sorry, plus, and then we have x squared plus 2x. Okay, all right. It would look slightly nicer as 2x to the 4 plus 8x to the 3 plus, but that's okay. Okay, so So now we have almost all basic operations. We have the addition of two functions, we have the product of two functions, we have the subtraction of two functions. What are we missing? We're missing the quotient of two functions. So the question is now, what do we do with the quotient of two functions? And that is what's called the quotient rule.
Why is that one not 2e to the x?
Okay, so 2e to the x, what do you mean?
Because it's e to the x times that function plus e to the x times that function. And you're putting them together.
So these are two different functions, right? E to the x times this plus e to the x times that. So I can factor out e to the x in both functions, right? And I get e to the x times and this whole thing. You're not convinced? Okay, so think about it like this. E to the x times 2x plus e to the x times 8x to the 3 plus e to the x times x squared plus e to the x times 2x to the 4. And then you factor out e to the x. Okay? Great. So thank you for asking. So quotient rule. What do we do with a function that is the quotient of two functions? Okay. And the quotient rule turns out to be a bit of a mess. You start by writing g of x, and then you write a derivative of f of x. So it's the product of g of x times d dx of f of x, which is a little bit similar to what we had over here. You see, it's basically the second, it's like this term over here, right? So the bottom times the derivative of the top, okay, minus the top times the derivative of the bottom. Okay, but we're not done. I wrote this long line because I have to divide by the bottom squared. Okay, so this is literally the function in the bottom squared. Okay, so let me give you an example of this so you see what I mean. The derivative of, let's say, okay, 2x plus e to the x divided by x squared plus 1. Okay? So we want to derive that, and we can write this as equal to so we're going to apply the quotient rule, and this is equal to first the bottom times the derivative of the top minus the top, this is 2x plus e to the x, times the derivative of the bottom, x squared plus 1. And the whole thing is divided by the bottom squared. Now the bottom is x squared plus 1, so this is x squared plus 1 squared. Okay, so this is equal to x squared plus 1 times, and what's the derivative of 2x plus e to the x?
2 plus ex.
Okay, so once again, we're not going to do it explicitly, but this is really the addition formula. So the derivative of a sum is equal to the derivative of this plus the derivative of that. And that is 2 plus e to the x. Then there's a minus. And then there is 2x plus e to the x multiplied by the derivative of that, which is 2x. And the whole thing is divided by x squared plus 1 squared. Okay, we can probably simplify this a little bit. I don't know, we could maybe write this everything out as, 2x squared plus 2 plus e to the x times this, and then the whole thing over here. We're not going to do it. It doesn't really bring us any intuition at this point. Just a question of simplifying a little bit. But I would like to point out that there are several risks involved in using the quotient rule. Basically, my advice is avoid it if you can avoid it at all. And if you can stay away from the quotient rule, just don't use it. What are some of the problems with the quotient rule? Well, first of all, you have this enormous quotient, right? So there's a lot of opportunities for you to if you have to break this down into two different quotients, you have to be careful with the signs and all kinds of stuff that can be created by this large fraction. Another problem that I see with this expression is you can forget about the minus and write it as a plus, or more dangerously still, you could forget about the order of the functions. You should remember it's the derivative of the bottom times the bottom times the derivative of the top minus the top times the derivative of the bottom. So if you screw up the order, you're going to get the negative of the answer. Okay? So basically, note, avoid it if you can. Okay, how are we going to, I'm going to help you avoid it in some way. How can we possibly avoid the quotient rule? Exactly. Once again, we can rephrase. This rephrasing thing or rewriting has become very useful for us in the past, and it will still be. So, example, let's see. So, for example, if you write the derivative of, let's say, 2x to the 3 plus x e to the x divided by x squared. You would think, well, that's the quotient rule, right? So you follow your nose. Well, not so fast. You're actually much better off if you first write this down as a product. Now, how can you write this down as a product? Yes?
You move the x squared to the top.
Okay, how do you move the x squared to the top?
You would just make the exponent and just make it negative.
Exactly. So dividing by x to the 2 is the same thing as multiplying by x to the minus 2. So this is x to the minus 2 multiplied by 2x to the 3 plus x e to the x. Okay. We can actually write this down as the, even before we use the product rule, we can simplify a little bit. And we can write this down as 2x to the 1, okay, plus x to the minus 1 e to the x. So now it's even easier, right? And that is equal to the derivative of the first function plus the derivative of the second function. Let's do that. So that's the derivative of, okay, let's I don't know if you want to see one more step, but no, I mean, it's obvious, right? The derivative of this sum is equal to the derivative of this plus the derivative of that. So the derivative of this is 2 plus, and now we have to use the product rule on this product over here. So it's x to the minus 1 derivative of e to the x plus e to the x derivative of x minus 1. Right? And that is equal to 2 plus x to the minus 1 times e to the x plus e to the x times, what was that again? The derivative of x to the minus 1? It's the power rule for n equals minus 1. Right? So it's minus 1 x to the minus 2. Minus 1 x to the minus 2. And this is equal to, if you wanted to rephrase this again, you can write this as e to the x over x. And then you write minus e to the x over x squared. Okay, believe me, it looks long, but it was because we basically wrote every single step. If you use the quotient rule, there will be a lot more opportunities for making a mistake. So do not use the quotient rule if you can. Okay, so let's do one more example and then we're done for today. But do you have any questions? You guys come up with some really good questions in the end of the class, so you can ask for it now instead. No questions? Okay. So one last example. Let's say that f of x is equal to square root of x times e to the x. And we would like to find the tangent line at the point x equals 1. Okay? So the hardest part of this problem is to find the slope of the function at m equals 1. And how do we find the slope of the function at x equals 1? We take the derivative, that's right. So first we find the derivative of square root of x e to the x. And just because it's today and I just talked to you for the first time about the power rule, let's write this down as a power, x to the 1/2 times e to the x. So this is x to the 1/2 times the derivative of e to the x, which is e to the x, plus e to the x times the derivative of x squared, which is 1/2 x to the minus 1/2. And that's equal to square root of x e to the x plus e to the x divided by 2 square root of x. Okay, so at x equals 1, I guess we can write this down notationally. It's a little bit messy, but we can write this down as at x equals 1, this is equal to square root of 1 times e to the 1 plus e to the 1 divided by 2 square root of 1, and that is equal to so e plus 1/2 e is equal to 3/2 e. Okay, So that is the derivative of the function at the point 1. We can write this down as m equals to that. Okay? And now I am going to, we're almost done, guys, sorry. So I'm going to remind you guys of a formula. If you wanted to have a line have a slope m and go through the point, let's say, x0, y0, what is the formula for the function? For a straight line that goes through the point x0, y0 and has slope m? M times x minus x0 plus y0. Okay, this is not a very important formula for today if you didn't know it already, but we're just going to use it. I gave you a lot of formulas today, so never mind this one too much. But f of 1 is equal to e is equal to to y0, and x0 is equal to 1, so y is equal to 3/2 e times x minus 1 plus e. That's it.